Hello, and welcome to this live IVT webinar in association with Parker Hannifin. The title of the webinar is How to Select the Right Linear Actuator to Achieve Greater Efficiency and Reliability. So my name is Tom Stone. I'm an editor of IVT International, and here I'm joined by Eric Larson and Jake Larson, who are not related as far as we can establish. We've had an investigation back through their family trees, many generations, but they are both Larsons, and they are here to talk very knowledgeably about this subject. Eric has over a decade of experience in the fluid power industry. His expertise lies in driving business growth and developing innovative solutions that meet customer needs in a dynamic market. And Jake, also hugely experienced in the design and manufacture of mobile equipment systems and components. Currently, his work focuses on the analysis, modeling, and optimization of Parker's e-pump portfolio, along with the design of electric-hydraulic actuators. So that's obviously very knowledgeable pair we have here, and they'll provide in-depth insights into the critical applications and technical considerations of using linear actuators across vehicle design. I mean, you know, with a huge number of people signing up to this webinar, a very popular, obviously vital part of vehicle design. So we'll crack on very shortly. Just to say before we start that this is live. There's a Q&A panel you'll see on your screen. So anytime you have a question, stick it in there. They'll be sent privately to the presenters, and we'll get to the questions at the end of the after the presentations. We'll get to the live Q&A session, and I'll share that. But any point you like, stick a question in there. You'll also notice actually beneath the slides there's a little 3 dots which you can drag up and down to make the window, the presentation windows bigger and smaller. You might want to make me a bit smaller and the slides bigger. I doubt the other way around. The session as a whole will last about an hour. So stick around to the end if you can, but it will be available also to rewatch and share after the event on demand. So I think that's all the housekeeping for now. I'll looking forward to these presentations, and without further ado, I'll pass over to you, Eric. I think you're starting, right?
Yes, I am. Thanks, Tom. And yeah, to Tom's point, we are not brothers, although we literally look like twins based on our bios. So moving forward, let's see. So many of you already know what the definition of a linear actuator is, but for those that don't, linear actuators are defined as devices that convert rotational motion into linear motion to move objects in a straight line. There's many different types of linear actuators. Below are just a sample of some of the more popular actuators. In the discussion today, we'll be speaking about the top 2, electromechanical and electro-hydraulic actuators, as those are most widely used linear actuators in on and off highway applications. Jake will talk more about these in a moment, but to briefly touch on the others, we have rack and pinion actuators, which convert rotational motion into linear motion using a combination of a gear, the pinion, and a linear tooth component, or the rack. Pneumatic actuators, as many of you know, use compressed air to create linear motion. Piezoelectric, a bit rare, but works by way of an electric voltage applied to a piezoelectric, piezo, which comes from Greek, which means squeeze, and material undergoes a change to the shape or size, and this deformation can be harnessed to create motion. And the animation on the screen just gives a quick visual example of a linear actuator in practice. So just to get your head wrapped around into the world of linear actuators, I wanted to show some examples of linear actuators in everyday applications. Linear actuators are located in all sorts of devices that we use every day. They're used in hospital beds to help raise and lower patients for both medical care and comfort. In cars, we use them daily for our hatchbacks to raise and lower them. One of the newer and more popular advances, I'm sure some of you are using right now, watching this webinar, standing desks. Standing desks have risen in popularity over the last few years as a great ergonomic design to help with potential back issues from sitting too long, all the way to having a walking treadmill underneath so you can both work and get some exercise in. Some of you may be lucky enough to have them open and close your curtains. No more having to get off the couch or out of bed to have to open and close the curtains. These are just a small sample of where you see actuators in your everyday lives. As we move into the future, we will continue to see them more and more every day. But for the purpose of the discussion today, we'll be narrowing our focus to just the mobile on and off highway space. As you can see from the pictures, there's application on skid steers and skid steer attachments. We see linear actuators being used on work trucks. They're used in agriculture. They can be used in underground and overground mining. There are many different applications that exist in these markets. Today, Jake and I will discuss what linear actuators are and what you need to consider when determining which actuator is right for you and your application to give you that optimal solution. So with that, I will turn things over to Jake, who is going to walk through basic considerations and take a deep dive on how electromechanical and electro-hydraulic actuators actually work. Jake?
Yeah, thanks, Eric. So today I wanted to cover the 4 different types of actuators that we're going to have in this discussion. 3 are mechanical and 1 is hydraulic. The first thing that you should consider when you're looking at a linear actuator for your application is a couple basic considerations based on fitment and performance requirements. So there are 3 primary considerations that every actuator needs to consider when you are designing for your application. First is stroke length. If you have an application where you have some mechanism that needs to be moved, the actuator must primarily be able to move the mechanism the desired length. Second would be force. Your mechanism likely is interfacing with some load, so there is some kinematic relationship between the distance and force. It is required to select an actuator that can transmit the amount of force both in extend and retract that your application needs. You also want to make sure that you are not selecting too large of an actuator for your mechanism because you have additional mounting or envelope issues that might come up. You might have additional efficiency issues that will arise due to too large of an actuator, or you could have way too much cost to make your product competitive to the market. And finally, velocity. That mechanism, it has to move a certain speed, whether it's as fast as you want or as slow as you need for precise position control. So those first 3 primary, those are questions that you should ask first for every application. There's also a number of secondary things to consider. These are not fully exhaustive, and these 4 that you see on the screen might not apply to your application. There's many others, but 4 that we see most commonly in this space. First would be design cycle or duty cycle and lifespan. Understanding how the actuator is used is really critical. Is this actuator only going to be used once a day and sit long periods of time in between use? Is it going to be used frequently for maybe a couple hours and then sit maybe over a weekend? Or is it going to be used continuously for 8 hours plus multiple days a week? That's really important to look at also because of thermal management and wear. Additionally, lifespan. Is this actuator expected to work 2,000 or 3,000 cycles, or is it expected to move in and out 200,000 or 300,000 cycles? Second would be voltage. As we are talking about electrified linear actuators here, and a lot of your existing mobile systems likely have some internal combustion engine, there may be a legacy hydraulic or electrical system that you are working around. Whether it is voltage or current, if you have an application for a linear actuator that has a certain velocity or force requirement, you need to make sure that the allowed voltage and current on your machine is actually able to do the work that the linear actuator needs to accomplish. So looking at, is it a 24 or 48 volt DC system, Or is it a 240 volt three-phase AC system that might be seen in an industrial application like a factory? Looking at that voltage and current is really important. Additionally, actuator orientation. Are there any envelope constraints that the actuator has to bolt into, or is there any retrofit or clean sheet constraints, such as base or rod mounts, pin diameters, flanges, etc.? Making sure that the actuator can be oriented and mount in a position is really critical for it to operate in your application. And finally, on this list, we've got environmental. Considering constraints such as temperature. Are we expected to operate in very low cold temperatures, such as below 0 degrees Celsius, or hot 80 degrees Celsius type applications? Are we experiencing very harsh vibration or shock loading? Are we going to be looking at applications where salt or corrosion are a risk, or even submersion underwater? Making sure that the actuator is able to withstand those harsh environmental conditions that you'd see in a typical on or off highway application is really critical to make sure that you're getting the best bang for your buck out of your linear actuator technology. And there's additionally a lot here that I will cover, things like efficiency, cost, or governmental regulations such as RoHS or functional safety. Those are secondary considerations that you may consider that your application requires. Looking at specific types of linear actuators. So the first we're going to cover is a ball screw electromechanical actuator. And we're going to call all electromechanical actuators from here on out EMAs. These have an electric motor that is coupled to a gearbox of some type that then transmits rotational motion to the lead screw. That lead screw has a series of small ball bearings that ride on it that are supported by a cage. And as that lead screw spins clockwise or counterclockwise, that cage extends or retracts, which causes a hollow rod to extend or retract from the EMA cylinder body. Typically, you're going to see grease or machine oil present to reduce friction and increase longevity of this actuator. And position sensing is something that is really easy to accomplish on these actuators because you've got a gearbox that has a known rotational to linear displacement relationship. So it's easy to put an encoder on the gearbox or the motor to know where the rod position is. One benefit out of these for the mobile space, they are pretty popular in the mobile space today, is that they have pretty low friction, which is good for high efficiency. Because you've got a series of hardened steel balls that roll between the cage and the lead screw, you get relatively low contact area and, again, low friction, which is great. However, those series of balls, because there are a series of motion that they roll through, do tend to fatigue and are not necessarily as reliable in high shock or vibration applications, and are likely not to last as long on a lot of mobile equipment where there's longer lifespan requirements, or the person's going to be operating the machine in a harsh application with shock or vibration. The next style of EMA is a roller screw, and these are available in both internal and external planetary styles. On the right image, you can see an external planetary style. Again, you've got an electric motor driving a gearbox, which either rotates the lead screw or the cage, depending on the style. And again, you're going to have position sensing that's relatively easy to implement due to the mechanical relationship between the motor rotation and the linear displacement. And you're again going to have some light grease or machine oil present to make sure that the wear and friction is as little as possible. There are lower contact forces in here because of the large surface area between the screw and the lead and the rollers, which does make your longevity and durability higher. However, those lead screws typically have more friction, so your efficiency is going to be lower than a traditional ball screw application. The final type of EMA that we're going to discuss is the belt-driven system. These are out in the environment. However, they are on more specialized applications. You have an electric motor that is going to drive some type of toothed sprocket that then runs a cogged belt. And that cogged belt drives a slide mechanism. As you can see on the right image, it's kind of a flat plate. And that slide mechanism is supported by linear bearings. There are a few moving parts in this system, so it is very simple. However, all of that force is transferred to that belt. So wear and durability especially can decrease as the lifespan of the actuator increases. You can get position sensing here. Again, there's a mechanical relationship between the motor and the slide mechanism. However, as that belt wears, error can increase, and these are typically not well suited for harsh environments, especially like corrosion and water ingress, because you have that linear bearing that has to be lubricated, and they can be difficult to mount in certain applications because they don't really telescope or extend, they just slide. The final type of linear actuator we're going to talk about here is the EHA, the Electro-Hydraulic Actuator. And these are kind of a hybrid between typical hydraulic systems where you'll have some pump, hoses, separate manifolds, cylinder blocks, and valving, and your traditional mechanical style. You've got a hydraulic pump that's directly coupled to an electric motor. And as that motor spins, you are displacing fluid, which flows through a series of passages and valves, which cause the rod to extend and retract. Now, one important thing to note on an EHA versus your traditional EMAs is that there is a rod differential in the cylinder. So a mechanical actuator is going to have identical extend and retract velocities and forces. However, an EHA is going to have a higher extend force than retract, and it's going to have a higher retract force than extend. Or retract velocity than extend, sorry. These are very robust and have industry-leading power density due to that hydraulic nature. And if you have a harsh shock or vibration application, you know, you're maybe on a ground engaging, like a scraper or something. If you hit an object like a rock, these actuators are really good at absorbing that shock load and relieving, where a mechanical system is more likely to have a really abrupt failure, like bending or breaking some component. So a quick summary of these four different types. Green is things that are positive. Orange is kind of average compared to the rest of them. And then red are poor. So ball screws, they really excel at good position control and cost. The force and speed are kind of in the middle ground. And then the life expectancy and durability are going to be on the lower end compared to some of the other options here. Roller screws, they have great force, speed, position control, and durability or life expectancy, but the durability and cost make them less than ideal applications for certain on and off highway systems. Belt drivens, they are awesome on cost and speed. However, the force due to that belt is lower than the other options, and the durability and life expectancy, again, are going to suffer compared to some of the alternatives. And finally, EHAs, they are great at force and speed, very durable. However, due to the complexity, there are some cost impacts due to an EHA that you're going to see, and the position control accuracy is less. There are some displacement measuring technologies for EHAs, but they're emerging or expensive or potentially hard to incorporate traditionally. So you can do position control, but the accuracy, due to that hydraulic nature between the motor and the cylinder, there's more variability.
Oops. Went too far.
Yep.
Oh,
So I'm going to hand it over
good.
to Eric here, and he's going to discuss a couple of the applications for these linear actuators in your on and off highway applications.
Yeah, so Jake just talked about, what are EHAs, what are EMAs, and really the question we get at Parker all the time is, how do I apply them into my mobile on and off highway space? So for us, we kind of segment it down to 3 different areas or zones. We have our 0 to 2,000 pounds of force, which is where we call our light duty. We have our 2,000 to 10,000 pounds of force, which we call our medium duty. And then you have your 10,000 plus pound range, which we call our heavy duty. And each, as different linear actuators that could work in each. So kind of working through from light up to the heavy about what would make sense for use in your application. So talking about light duty applications, if you come to us, we're looking at light duty applications where, again, it's under 2,000 pounds of force. The duty cycle is relatively light. We say 25%, but usually it's a lot less than that. And typically manufacturers that are using these types of linear actuators, they're shielding it from potential environmental issues, whether it's corrosion, whether it's water immersion, shock and vibration. And then usually OEMs are looking for the low cost solutions for that. So in this space, there's really 2 different linear actuators, based on what Jake talked about on the construction of the different types of linear actuators. The ball screw EMA makes the most sense here. Really good at that low force, that low duty cycle. Again, if you're able to minimize that exposure to those environmental concerns, it's the perfect fit for this, and it's going to be the most cost-effective solution. However, just keep in mind, if the application is exposed to shock or vibration, then you might want to consider a heavier duty actuator. So in this respect, we would look at the Electro-Hydraulic Actuator, or EHA, but it will actuate slower at those forces under 2,000 pounds of force when you are comparing it head-on compared to the ball screw EMA. But again, it overcomes that concern with subjected potential hazards. But the drawback is, of course, it's going to be a little bit more costlier than the ball screw EMAs. Moving up, medium duty applications. These, again, 2 to 10,000 pounds of force. Our duty cycles are expected to live a bit higher, although 40% is on the much higher range. Really 25% is that good area. It's going to be exposed to potential environment issues, like you're kind of seeing on the right in that picture. And now OEMs are expecting them to be smarter, to integrate into their system, whether it's with the J1939 or CAN open protocols. So with this, you have a bunch of different options, a bunch of different attributes that you can kind of look and weigh the pros and cons between. Again, starting with the ball screw EMA, you're going to win on cost. Cost is still going to be a lot less than the other potential linear actuators. But now that you're over 2,000 pounds of force, you're into that medium duty, it's going to be operating a lot slower than the EHA and the roller screw EMA. And there's going to be a much lower life expectancy. In fact, we've seen that it's exponentially lower as you continue to increase it over 2,000 pounds of force. And again, it's going to be susceptible to those potential environmental hazards. So really in this zone, the EHA is that perfect fit for you. It has a fast actuation speed relative compared to the ball screw EMA. It has a high life expectancy. It can handle all sorts of potential environments because of its construction to what Jake was talking about earlier. And again, it can absorb all those potential shock and vibration. Lastly, because we're in the middle, we can start to look at more sophisticated, look at the roller screw EMA. That is a potential as well. It can handle those higher forces. It has the fastest actuation speed, has a high life expectancy. But again, it's more industrial. it's susceptible to those environmental hazards, and it really has a high cost due to its construction.
Hey, Eric, can I
Yes.
jump in just a second? Because a couple of questions just came in before you move slides. On the efficiency, I guess they're talking about power efficiency. A couple of questions came in on, can you rank efficiency of the different solutions, or are they about the same?
So what we've noticed through our own testing is that 2,000 to 2,400 pounds of force is an inflection point between the ball screw EMA and the EHA. Below that 2,000, 2,400 pounds of force for that extension load, the EMA, the ball screw EMA, is more efficient. But once it gets to that, where we see that inflection point where both the speed rapidly decays, the life rapidly decays, the efficiency also takes a huge hit. That's really where we get that fluid power density in hydraulics. So through our own testing, we have seen an efficiency gain between that 2,400 to what we tested up to about 5,000 pounds of force. We've seen that we are 3 to 5% more efficient. So that's 3 to 5% less amp draw.
That's great.
Great questions. Yeah. So moving on to the heavy duty applications. These are what we would consider force loads above 10,000 pounds of force. And the duty cycles range from anywhere between 0% to continuous. However, most OEMs are expecting it to be continuous duty, and they are expected to perform in all types of environments and potential hazards, as shown with the excavator on your right. And really, as an emphasis right now, we're still looking at low cost solutions. That's what the manufacturers are looking for. So just kind of looking at the picture in front of you, you can count 1, 2, 3, 4 hydraulic cylinders on that. If you replace that with an EHA or an EMA, that's 4 different EMAs or EHAs that you have to replace. And to do that right now would be very costly compared to what's available today. So if you were looking at using one of these, there are EHAs that meet the needs here. I mean, they can handle that high force, high speed. However, it's really hard to fit them in. The envelope size is a huge issue. They are costly. We've seen that roller screw EMAs have also been looked into in this potential market for these applications. But it still has the highest force, highest speed, but there's the environmental concerns. And then of course, it's very costly in order to do that. So Jake's going to talk a little bit about, where we see things going as of today. So I will turn things back over to Jake.
Yeah, thanks, Eric. I think the question does come up, hey, when can I get a linear actuator for my large piece of equipment? And as Eric kind of mentioned, there are some emerging EMA and EHA technologies that can work, but from a architecture of the hydraulics, like what do we see? What do we see as a solution for these applications? Current state, you're probably familiar with. You've got some internal combustion engine that has a centralized hydraulic architecture. So you're running some diesel or gasoline engine at a high idle that is directly coupled to one or more hydraulic pumps for the work functions. You've got a series of hoses, valve blocks or manifolds and cylinders, and you do have some poor efficiency due to compounding losses. You've got the efficiency of the internal combustion engine, the pumps, your flow losses through all your valves, and you've got a lot of things that are less than desirable from a noise issue. Your hydraulic system can be noisy. Your internal combustion engine can be noisy. You've got emissions from the internal combustion engine that might be undesirable due to government regulations or working in a application that emissions is really non-desirable, like indoors or underground mining. So future state, there are some electrified solutions out there for that future state, but we do see them likely being more in the centralized architecture. So you're going to see some type of electro-hydraulic pump called an e-pump. That's kind of a Parker logo for that. And we've got one e-pump that's running the primary work functions. You've got a single pump. You might see some linear actuators for select functions. The good thing with the e-pump system is that you're leveraging a lot of your legacy cylinders, hoses, and manifolds, but you do have fewer losses across our pump and piping due to some advanced controls that you can implement. And optimal state. Absolutely, an optimal state with a decentralized architecture, an EMA or an EHA in every position. That is a great place to be, but we're not there yet. You can do some great things with controls and energy regeneration, better precision, noise control, things like that. However, from a cost envelope perspective, the market for EMAs and EHAs does need to catch up for these. Now, not saying that there are not opportunities for linear actuators on heavy pieces of equipment like an excavator. You can look at things like hydraulic thumbs on a bucket for an excavator, or options for outriggers on a crane, or ladders for access on different pieces of equipment. There are applications, but they're going to be typically more for auxiliary functions. And there are definitely opportunities in the future, like I mentioned, but I might hold off speccing a linear actuator for a very large piece of equipment like you see on the screen. However, I don't want to pour too much cold water on the linear actuator space for mobile equipment. There have been a lot of advances lately that make them attractive for those auxiliary functions and those medium duty cycles. So where have we seen the advances recently in the linear actuator space? So first is the communication. CAN bus is a big thing, and we're seeing more and more linear actuators adopt J1939 or CAN open. It really allows precise control, wiring simplification, and also really good data monitoring. So, IoT is a big thing in the marketplace today. You can do really advanced hour logging, performance, duty cycle tracking when you have a linear actuator that has CAN bus enabled. Position sensing, that's a big one too. As we see more and more smart agriculture or earth moving applications, GPS, things like that, knowing where the position of the linear actuator is more and more important. And recently, position sensing has become widely adopted on the EMA space, and it's becoming more and more prevalent in the EHA space. Also, technologies on the motor side are making it a better option for the mobile space. Traditionally, low-cost brush motors have been used on most EHA and EMAs. However, the advent of brushless DC, such as a servo or VLDC type, have really allowed longer longevity, better efficiency, higher power, and they make a lot of sense for these mobile spaces. Environmental durability, so things like IP67, we talked a lot about shock and vibration, corrosion. A lot of these traditional EMAs are more for the industrial space, so they're in a building or maybe on a light duty application. They're shielded, like Eric was mentioning, from the harshest applications. Linear actuators in general, especially EHAs, are emerging that can really they're robust for those environmental applications. And additionally, industry standard mounting. A lot of our applications for mobile hydraulics obviously already have some type of hydraulic cylinder on them. And a lot of EMAs and EHAs have very special base and rod mounts. So you might have to make pretty severe design changes to your mechanism if you're going to retrofit an EHA or an EMA into an existing hydraulic cylinder application. So you're seeing more and more linear actuators have industry standard mounting like NFPA. So bolt-on ends, threaded rod ends that allow you to get custom clevises or greasable spherical ends to make your EMA or EHA bolt into your application versus having your application work around the constraints of the actuator. Additionally, there's been a lot of hydraulic circuitry development in the EHA game lately. So if you're familiar with hydraulic systems of the past, you've got a lot of different circuits for a lot of different applications. And EHAs, due to their hydraulic architecture, do allow a lot of new circuit or a lot of existing circuitry to be incorporated. So you've got a traditional load holding circuit on the top left, something that might be used in a dump bed on a on-highway truck or a UTV. So you have some type of variable load due to soil or debris that can be loaded in that box. And you've got a zero current load hold where you can hold the load up or down. You've seen back pressure circuits. So these are great for steering or tilt control where you've got some resistive load and then you've got a lock in a position. Bottom left there, counterbalance. You might be aware of issues on hydraulic systems where if you've got a tension load and you're extending, you can overrun valves or the pump. Typically, counterbalance valves are used to have more smooth or safe operation. Those are things that you can get in EHAs now. And float circuits. So that is something like if you've got a snowplow blade or some type of ground engaging device where you might want to load hold in a retracted or extended position and then unlatch, per se, the device where you can follow the ground conditions like a road or a surface in the soil. Float circuits allow you to do that. And I'm going to hand it over to Eric to discuss some Parker advances in linear actuator technology.
Yeah, so a lot of the things that Jake just talked about, those are things that we have learned, and those are things that we are starting to incorporate into our next generation product. So this is what we're calling our Parker Force Command. It has an integrated J99 can open controller, again, fitting what the mobile market wants with the total system. Brushless motor has much more advantages over your traditional brush motor. It's more efficient than a brush motor, longest lasting for just 2. We'll talk a little bit more about why we put aluminum cylinder extrusion as a feature right here on the next slide. A big question we get from distributors all the time is, why don't you conform to the NFPA rod end? And as Jake said, we learned that we need to do that. So now we've added a number 4 short male, conforming to those industry standards, so it's much more easy for fit up. There was a question that came into the chat, great question, regarding position sensing and we do have that now. We've been in collaboration with the University of Minnesota in designing a non-ferrous absolute position sensor. This sensor can basically tell where the magnet is in space because the magnet is on the rod or on the piston, and it can track that and gives us absolute position feedback, which we're able to get now by using the J99 can open. And then again, we got the NFPA conforming base mount. And then really what we do really well here at Parker is our pump, our reservoir, our really high efficiency in our pump, and then the hydraulic circuitry. So everything that Jake just talked about with the 4 different circuits there. In our past generation product, we had just a load holding circuit and a back pressure circuit, but now we have the float circuit and the counterbalance circuit as well. I mentioned we talk a little bit more about the aluminum extrusion, and here's why. Before our old, or not old, but our current EHA has a 4-inch, 6-inch, and 8-inch stroke length. That's it. Now we have the ability to go between 6 and 18 inches of stroke, and we can just cut the length, so we can do anything between those 2 parameters. And then also bore size. We've been asked, we need something that can handle a bigger load. We're doing that now. We have a bore size of 1.5 inches and 2 inches, which gives us an ability to extend up to 9,400 pounds and retract up to 7,400 pounds and retract. As machines become more electrified, higher voltages are being required. And we've upped our game here. So now we offer a 24 and 48 volt DC.
Yeah, and I wanted to talk a little bit about where do we see future advances in this linear actuator space going. So higher voltage and higher power, that's definitely something that we see. Although we do offer up to 48 volts, we do see, that 200 to 1,000 volt three-phase type applications, especially in the mobile space, getting bigger and bigger. Also higher power on that motor. So things like over 5 kilowatts for those very large applications. And as you have a larger electric motor, it allows you to have higher speeds, increased force, longer strokes, and elevated up to continuous duty cycles. So these top 3 rows, they're really going to address some of those applications more on that heavy industrial side, like that excavator, for valuable solutions to the customers. We also see some things on the bottom row there, like sharing flow between multiple cylinders with a single power unit. So we see a lot of applications where there's only 2 hydraulic functions, let's say a bucket lift and a bucket tilt. Having one EHA with an auxiliary power that can offboard is something that we do see as an option in the future, or synchronizing motions of actuators. So if you've got 2 to 4 actuators on a single device, you can pair them up to get higher forces, and you can move them in synchronous motion. Or if you've got like an outrigger application on a piece of equipment with that's parking on a uneven terrain, those actuators can talk to each other and the master controller and lift and level that device. And finally, functional safety. As we get more and more autonomous vehicles, we're seeing OEMs ask more and more for functional safety, just to make sure that the users and people on the job site are being safe and that there's no safety concerns or injuries caused because of products. So these are things that we see these linear actuators adopting more and more in the future.
So lastly, just want to touch on what we have available. So at Parker, we have a broad range of products. From mobile electronics, we have displays, we have controllers, we have joysticks and sensors to meet your on and off highway needs. From an EHA perspective, we touched on just now on our new Force Command, but we also have our current Force EHA, or as we knew in the past, the Compact EHA. We also have the HAS, so for those higher force loads as well, HAS standing for Hybrid Actuation System. EMAs, we have a wide breadth of different electromechanical actuators as well, from our XFC to our ETH, which are our roller screws, to even the belt-driven EMA that Jake talked on at the onset. So with that, if you have any questions for us, I'm sure Tom will take over for that in a second and running the Q&A. But if you have more questions for us specifically, please either scan that QR code. Yes, we did double check with our cameras before this, so your phone can take a picture of that QR code. It will take you to the website that's listed there, or you could just type in that website for more information on what we talked about today. And if you need to get in contact with us, there is a registration form on the website as well if you have any questions or comments for us. So with that, we will turn things back over to Tom.
That's great. Thank you. Thanks so much, Eric and Jake, for that really informative presentation there, really helping to crystallize some of those concepts and technologies. And I learned a thing or two, including EHA, because I've read about these things and I've, I always call them EHAs, but apparently not. Apparently I was getting that wrong. This is the beauty of hearing someone talking about it. So EHAs is obviously a key part of this. I've got a quick question though. What is the limiting factor in the stroke length for these EHAs or EHAs?
Yeah, I can take that. So when you have larger and larger forces, buckling of the rod becomes a concern. So our Force Command product does go up to 18 inches of stroke. That has a 1-inch rod. If we want to see something maybe like a 24-inch or longer stroke, a larger rod would be required. That's something that is potentially feasible, but that would basically be your main thing to look at, is like, what is the rod size and what are the loads, and doing a quick like analysis on understanding that rod diameter to buckling relationship.
Okay, got you. We've got some great having that QR as well, by the way. Thank you for that, because that's, of course, if you're watching this on demand, you can still take part in the Q&A by using that. But yeah, some questions pouring in from the floor now. How does solutions compare by total weight for off-road application force demands? So have we got weight differences there? At
this point, it's the ball screw EMA would probably be the lightest, but it's a hard question, because really it depends on the application, what you need, because there's so many different configurations of each. But if I was just to take a standard, I'm just going to throw out there a 12-inch stroke, the EMA is going to be about 5 to 6 pounds less than the EHA. So that, just to give you a baseline of what that would look like. That's great, thank you. We spoke about efficiency. I jumped in during the presentation, which was great. Nick Carp asks, are there any specific steps being taken? Oh, that one's disappeared from my screen. Hang on, I think it's gone into my other tab. For safety, I think he was saying. I'm not sure whether this is just, but I think it was about safety. Specific. Oh, there it is. Let's come back. Specific steps being taken to help customers comply with functional safety requirements. So this one, it's a very, very common question that we are getting every single day. For the products that we have currently available, or even the Force Command, it does not have that functional safety requirement yet. There's so much we need to learn about that. We're aware of it. We know what we need to do, and we're already planning on the next generation of product that's going to be functionally safe. Right, thank you. Nathan Bong asks, how would you rank each type of actuator for the noise level?
Yeah, I can take that one. So we've noticed, depending on the load, especially, the noise has changed. So we've benchmarked and tested a lot of ball screws and compared them to our technologies. The type of the noise quality is a little bit different. A ball screw, you get more mechanical, maybe rattling noise. And an EHA, you get more hydraulic flow noise. So defining the type of acceptable noise is very nuanced. I'd say they're generally the same, but like I said, it's going to matter a lot on the force that you're looking to output. Ball screws are likely to be a little quieter at lower forces, but we've noticed that as you increase in force, they tend to get a little bit louder, and the EHA seems to stay pretty level as the force range varies. But they are quieter than a traditional like internal combustion engine running a direct coupled pump with a series of valves and hoses.
Great stuff, thank you. Any plans on making larger bore EHAs without getting into a more expensive Haas unit?
So it's being considered. What you have to remember is the bigger the bore, and we have bigger rods for that, we have to displace that rod volume. So you have to have what we have in our Force Command. We have an accumulator there that's absorbing all of that displacement, that volume of that, and you have to make that bigger. And a question becomes not only is there the fitment issue, but it's the repeatability. Once you get above that 10,000 pound force range, the different types of loads varies tremendously, and to make a product that can fit all those different forces, all those different force loads, and make it economical, I can't say the word, be able to make it for a reasonable price. That is the question, and it's something that we're beginning to look into and starting to brainstorm about how we can make that happen.
Thanks, Eric. Thanks, Todd Steyer, for that question. Randy Foot asks, is the force unit currently available through distribution? If not, when will it be available?
So we are currently taking prototype orders, and we are looking to launch the product this winter.
Excellent. I have another one here. In mobile applications, temperatures of -20 are possible. Can ball screw actuators withstand these low temperatures? Oh, have we frozen up there? Are we all right? Are we? Oh no, we have literally frozen in the -20 temperatures. So sorry. Did you get that? Balls are. It's particularly about the ball screw actuators. Can they? What's the lowest temperature they can operate in? Is that a limitation?
Yeah, I can take that. So it certainly can be. As mentioned in the construction, there are grease and light oils in ball screw applications. It's kind of a common misconception that EMAs are leak-free. There is some level of lubrication present. So EHAs are impacted as the temperature gets colder. Obviously, the oil gets thicker, but EMAs are still subject to temperature variation. The grease and oils do get thicker, the friction increases. So they are likely to be a little less impacted than EHAs, but there are still impacts. I'd have to look exactly on all the competitors out there for like what the minimum temperature rating is. I'm familiar with a few that are rated to those lower temperatures, but it's definitely not something that's widely offered.
Yeah, I just did, Jake, and you are correct. Yep. So they are able to get down to -40 F.
-40, right?
Yes.
Wow. Okay, and there was another supplementary. This is on. Funnily enough, both came in about the same time. Another question on upper temperatures as well, lower and upper. Is that? Do you know? Have you got the information at your fingertips there now, Eric? On that upper temperature?
I do, and yeah, it's so EHAs and EMA is very good at. Everyone pretty much advertises up to 150 degrees Fahrenheit. Some will even go greater than that, but really everyone kind of restricts themselves at about 150 just because of the motor temperature.
Okay. How much of a problem is there in keeping roller screws lubricated? Is that an issue?
Yeah, we've seen in our testing the roller screw does tend to wear, ball screws tend to wear. Roller screws as well. You've got mechanical interfaces sliding back and forth. There typically isn't like a pump that you might see in a lot of mechanical systems that splash lubricating everything. So you're going to rely on whatever grease or oil is in there during assembly to get into the high friction locations where it needs. So if the lubrication slides away, you're going to start seeing increased friction wear. That is a benefit of the EHA, is that because you've got a hydraulic-based system, your lubrication is always present as you move in and out the rod.
Great, thank you. And are there issues? What are the issues with syncing the EHAs in tandem?
Yeah, absolutely. So EMAs, because there's a mechanical link between the motor speed and the linear displacement, you have a good understanding of where the rod is. However, on EHAs, because there is a hydraulic pump, there's a little variation in the flow. There might be some temperature differences. If you've got different loads on, one side of the device or piece of equipment than the other, one actuator could move faster than the other. So by implementing that linear position sensor that our new Force Command product has, you can see in real time where that rod is. And using the CAN bus, you can transmit that back to a master controller. Using an algorithm, you can command a higher or lower PWM for the motor, depending on what side is moving out of sync, and you can speed up or slow down one of the actuators as the loads and positions change.
Excellent. What will be the leakage of these actuators? Maybe that varies between them, or maybe there's not much at all. Can you quantify that? That's quite an open-ended question, I think.
Yeah, I can take that. So the leakage on an EHA, there's obviously oil present. However, it is a sealed system. Unlike a traditional distributed hydraulic system where you've got numbers of hoses and fittings and valves that can loosen up or fatigue over time, an EHA it's all self-contained. So there are a lot less opportunities for wear, abrasion on hoses and things like that. So leakage, it's hydraulics. There's always a chance for some leakage, but like I said, the EMAs and whether they're greased or oiled, again, there is a opportunity for leakage there. It's lower, but it's not zero.
All right. You mentioned earlier the ball screw actuators are poor at vibration. Why is that?
Yeah, so the ball screws, because it has a number of ball bearings, they can be subject to wear or very high contact forces. So if you hit an immovable object, as mobile equipment does often, the balls or the cage or the lead screw have to take that full force with a very sharp, high, short duration impact. So all those mechanical contacts are absorbing that load, whereas an EHA has typically a thermal or a safety relief valve that's more similar to a legacy hydraulic system. So if you do run into something, that actuator provides some give. We have seen some linear actuator in the mechanical game, ball screw, have some type of like rubber damper actually present. And that does seem to improve the durability when you have a shock or vibration type application. However, we've noticed that rubber can fatigue, or as you have oscillating loads, that rubber tends to give a little bit. So you do have lower position accuracy because the pin-to-pin lengths are actually changing a little bit as that rubber or polymer isolator absorbs those shock loads.
Excellent, thank you. We've just got a couple of minutes left. Another quick question here from. Oh, hang on, I think that one disappear. Oh, I thought I saw one pop in. Here's another one. How soon can we expect? I think actually we sort of covered this, but how soon can we expect advances in linear actuator technology to handle heavier duty applications? We spoke a little bit about that at the beginning of the Q&A section, but do you want to address that?
Yeah, so again, it was very similar to the question that was just asked. It's really, for those higher power linear actuators, and it's being able to design something essentially to, what I was saying earlier. It's what are you willing to pay, and it really comes down to can it fit in it, and can it have the same performance requirements as what we're using today. So that's really the questions that need to be asked, and really we see this coming within 5 to 10 years. So it is coming, but just not today.
That's great. And here's maybe a good one to finish. I mean, you mentioned some of the other sort of industries that this is being used in or has potential. What's the future? Where will linear actuators take us, and what other uses might they have in the future?
Yeah, so one of the early ones actually, it was not on and off highway for solar tracking. So energy, we'll continue to see a need for them. Definitely a lot of linear actuators to be able to track the sun. We'll continue to see it mining over and underground for both of those. Industrial, there is some need in industrial markets as well for potential dock or ramp lifts, even lift tables. We're seeing that today to get rid of the central hydraulic power units. And then, of course, recreational. We do a lot of work in the recreational marine market, whether it's wake gates, and then we'll probably see that in hatch lifts as well. And these are just a little samples. There's a lot more out there that we haven't even covered now. And we're just learning about these potential opportunities and applications as we continue to move forward.
Absolutely. And it all feeds in, all this technology and different industries feed into one another, and we can learn from each other. And this, as you say, this technology just starting out really, and very exciting to see how it develops. So we're just about out of time, but thank you so much, Eric and Jake, for those really interesting presentations. Thank you, everybody, for logging in. As I said at the top, this is available on demand, so please feel free to watch again, get in contact with Parker via the link, and we'll hope to see you all soon.
Thank you.